and instrument.
That's,
and
it's
coordinate
expanding.
with them how to figure out
But
what's
this
going on.
shows that the
And
expansion
fix it
rate
or
is
not.
accelerating.
Is Hubble's
It's getting bigger all the time because of dark energy, which is a complete mystery.
to be able to?
If we figure that out, we all go to Sweden.
It really has to
Pick up the prize.
You have to have the energy to keep the gyroscope spinning, and you have to re-energize those because you were using the energy and to move them around.
Is there significance, any mapping significance to temperature distribution that you've shown us there?
Yes,
In other words,
never worked on
you have
the
Hubble,
Hubble, but
Yeah.
I
but why
think
you
I
have to
understand a lot
even
of
at
the
that
issues.
minuscule degree.
Well, every point on the sky is
I
at
can
a different
understand
temperature.
conceptually what had to be done.
This is what we
How
inherited
that
from the
gets
early
implemented.
universe.
Yeah.
That
The
just-
why is, we don't
It just seems
know.
impossible.
The reason that the temperature variation is as it is,
teacher was fabulous.
Thanks for telling
we
me.
think we know. The answer is quantum mechanics. Quantum fluctuations in the early universe imprinted
And it all
the
comes down
variations
to
that we see in the microwave
the teacher.
background. Like, can we calculate what that looks like? What it should be? No,
It was a math major.
because it's a kind of a random process.
Okay, thank you.
And
Okay,
differential.
so let's reconvene, because we have a couple of great conversations that I don't want you to miss. There are two things to talk about. One is when we, they'll come in a second. One is, what is the experience we have if we become astronauts? I just a thought experiment where we get Earth and Moon and the Sun out of the way, and we go out in space, and we want to measure the microwave background, which is what these spacecraft that I've been talking about actually do. They look, they have a pattern, they sweep across the sky like this, and then they rotate and they sweep across the sky, and gradually they build what you would experience as the interior of a sphere. I mean, you think about what you're experiencing right now when you're looking up here. If the walls weren't here in the way, your life experiences, you're inside of a sphere, and light comes to you, and you can look in any direction. You're unimpeded if you're an astronaut floating in space. You appear to be inside of a sphere, and what you measure is essentially a painting on the interior of that sphere. And that sphere, the distance from us to that surface is the distance from us to when the universe became transparent. Roughly 13 billion light. It's looking back 13 billion years. So the way, now there's some confusion because of a chart I showed, this one. This looks like you're on the outside of a sphere, right? The only reason this is depicted this way is to illustrate this kind of mapping projection. That is, if you take a sphere of Earth and flatten it in a certain way, you get this Mercator projection. If you were looking at a sphere of the cosmic microwave background and flattened it, you get this. In reality, the measurements are all made as if you're on the inside of a sphere, and you just have to look everywhere and collect the data and write it all down. And then you can turn it into something that looks like this. The other point that came up is how many dimensions are depicted by this drawing. So here's the problem. We're trying to depict the universe and spatially, and we're trying to depict time on the same drawing. So we have a time dimension, and we have space, but when we add time to this, we're using up a valuable resource, namely one of the dimensions that are available on a flat surface. So all that's left is we can make this kind of a projection like our artists and architects do. We have two dimensions here. If you were looking into this, you would see a circle, and there's a distribution of galaxies. And if you move closer to the Big Bang, you'd see earlier galaxies, and you would be progressing this way. But we can't do that in 3 dimensions and draw time on it as well. So if you see this as layers, like disks, and each disk is at a different time, as my hand moves, I'm going to early and earlier time. That's the best we can do, given that we view things on flat surfaces. Now, what can change this is virtual reality. I've had a couple of experiences with it where you put the goggles on and you suddenly, wherever you point your head, you see a different thing. And you can be on the inside of a sphere that shows, for example, my experience was at a design review for a spacecraft, where the complexity of the spacecraft is hidden by the outside, and they gave us goggles, so now, okay, you can use a joystick, you can zoom into the very interior of the spacecraft. You can look this way and look this way, you can look all around, including down and behind you, you can see all the details. So visualization is a problem if we're using a flat screen. We have to kind of ignore that. So we've suppressed one dimension here.
And if you took these discs and moved in the direction of Big Bang, they get smaller and smaller, wouldn't they?
Yes.
It's more funnel, that picture's deceiving, it's more conical or funnel-like.
Well, no, this is drawn to try to illustrate exactly what's going on. That we have the Big Bang, and very early, we have this explosive inflation. And then we have a long period of gradual increase in the size, but then it has a curve to it right here. See that curvature? That shows that the rate of expansion is getting bigger. The rate is getting bigger. So the universe is getting bigger, and the rate of getting bigger is getting bigger because of dark energy. Okay? So we have some limitations because we view things, and when you think about it, if I took a picture right now of this group and showed you the picture, I would have projected the 3 dimensions that are really in the room onto a 2-dimensional photograph. This is a constant problem in visualization, and I'll tell you what the professionals do. They don't look at pictures, they use math. Because you can depict everything using multidimensional math that we can't draw on the screen. It's an unfortunate limitation. But as I say, virtual reality make things better. So let's carry on. Did that help?
Yeah.
Katrina brought this up, and I want to make sure.
Thank you.
Okay, so there is detail here on this page, if you want to read the detail, about the problem of getting rid of the local microwave background so that we can actually get this. Okay. This is the same kind of thing. Here's COBE, WMAP, and look at the detail Planck gives us. So here are the Nobel Prizes. Penzias and Wilson for CMB from the ground, Mather and Smoot from CMB in space. Now let's talk about cosmic microwave. Oh, the B is missing. Oh no. Here's the first thing we get. The clumpiness of this tells us the geometry of the universe. Last time we were together, I made the following point, that there's a difference between geometry and shape. This is a flat piece of paper. Everybody would agree, professional mathematicians and we agree, this is flat. That is, the geometry is flat and the shape is flat. If I roll this up, oh, and if I drew a triangle on here, that triangle would have 180 degrees. You might remember that from your high school geometry. If I roll it up, the average citizen would say, well, that's not flat. But a mathematician and a cosmologist would say, oh yeah, it is. Because if I looked in there and measured the angles of the triangle I drew on the paper before I rolled it, still 180 degrees. So this is not a flat shape, but it is a flat geometry. And there are other geometries that are possible. One is called open. It looks like the saddle you put on a horse. And then there's the closed geometry where not only is the universe have a radius, but that the geometry is spherical. This is mind-bending, I know. Fortunately, this is the one that seems most likely. And up until about 2 months ago, everybody was content that the universe is flat. It may not be a flat shape, but the geometry is flat. There's a little cloud on the horizon now that comes from the Planck data. Because, as I said, the data stopped coming in 2013, but people are not done chewing on the data. And there's a little hint that there's a subtlety that we have not dealt with, so that's coming. So the idea is, if you look at the Planck, the cosmic microwave background, and measure the distance between the hot spots and so forth, if the universe were open, have this geometry, the spacing between the bright and hot and cold areas would be different than if it's closed. And right now, the spacing appears to lean in the direction of flatness, which is conceptually easier to chew on. I mean, I don't know how to think about an open universe. By the way, if you want to participate in chewing on the Planck data, you can join thousands and thousands of other people, including one person in this, that looks like the Seychelles Islands. Where you just donate your home computer. When you're not using it, it sucks in data from various researchers and does computations on behalf of trying to understand what's going on with the cosmic microwave background.
How can they avoid being hacked?
You know? Yeah, maybe, but, so here's another depiction of the geometry issue. Once again, how clumpy is the picture we're looking at, and does it give us information about which of these geometries are right? Here's the open, these are reversed somewhat. So this says open, whoops, this is the open universe. And if the universe was really open, the distance between the hot spots would be bigger, would appear to be bigger than what we observe. And if it was closed, that have more spherical shape, clumpiness would be more dense than we observe. And it's like Goldilocks, we're right there. And this is one way to talk about the question that Katrina brought up, is when we look out into space, if we're looking into microwave wavelengths, we're inside this sphere. And various distances contribute different types of light to what we observe. The closest ones show us the modern galaxies. The light from the Big Bang, or the cosmic microwave background, comes to us like we're inside of a sphere that's being illuminated by 2.7 Kelvin light. And incidentally, 2.7 Kelvin is really cold. It's only 2.7 kelvins above absolute zero. The early universe was really hot. So how is that reconciled? And this is what Alford dealt with in his dissertation, that the universe has expanded enormously in the last 13 billion years, and the light that was created at high temperature gets stretched on its way as the universe expands. It's like having a slinky, and you just keep stretching it, and the wavelength gets longer, which is equivalent to saying the temperature gets lower. So by knowing that the background is at 2.7 Kelvin, we can estimate the temperature when the universe became transparent. And it exactly fits with what we measure in a lab every day. If you take a hydrogen in a lab and you bombard it with light, with I'm going to use some terms that are alien to you, but you'll get the idea. If we bombard the hydrogen in a container in a lab with light at 13.6 electron volts, which is X-rays, the hydrogen gets knocked apart. It's called its ionization. And that's exactly what the theory and the measurement we currently do in laboratories. Every college chemistry student does that experiment. It all fits. When the light in the universe was at 13.6 electron volts, which is X-rays, there were no hydrogen atoms. And as soon as the temperature dropped and those energy levels went down a little bit, every proton that found an electron, it got married. Now we come to really stupendously important stuff. The drawing, let's go back, so I want you to have a clear picture of this cosmic microwave background, and it has hot spots and cold spots. Now what we're going to do is a mathematical technique where we're going to measure what is the average distance between, if I start at this point, I'm going to measure the temperature difference at every distance from this starting point. And then I'm going to move that starting point a little bit, and I'm going to do that same experiment over again. I'm going to keep doing that, and I'm going to collect data on what's the distribution of hot and cold spots in the cosmic microwave background picture. Whoops. And this is what we get. This is a different spatial scale. So the moon is kind of over here in terms of how big it appears to be on the sky. And this is getting smaller and smaller as we go to the right. And a lot of the information is here at about 1 degree. That is, the distance between hot and cold spots is peaked right up here. And then there's a dip, and there's another peak, and there's a dip, and another peak, and a dip, and so forth. So that comes from doing a mathematical analysis on the cosmic microwave background picture. Now,
What do the vertical lines on that picture mean?
oh, this is error bars. So at this, for example, at this point right here, the amount of data collected at this angle has a lot of variation, a lot of uncertainty. We're going to fix that in the next slide.
Thank you.
Here's the next better version. So this has black dots. See the black dots? These come from WMAP. I already showed you that spacecraft. And then we have a series of measurements done from the ground, including this brilliant experiment called Boomerang the Australians did. Here's what they did. If you go south from Australia, you come into the region at high southern latitude, close to the South Pole. And there's, in that area, there's a thing called a circumpolar vortex. That is, the wind goes around the South Pole consistently, just around and around it goes. So the Boomerang guys built a tool for measuring the cosmic microwave background, put it on a balloon, flew it to high altitude, and placed it in the circumpolar vortex. And they say goodbye, and it leaves. And it goes around the continent of Antarctica and comes back. It takes about 2 weeks. And then they command it to come down, and they have the instrument, if they have to repair the instrument or improve it, and they made measurements, so their stuff is green. So you see these green bars here. And once again, the vertical tells us the error bar. But we're going to fix that. So we have a bunch of ground-based measurements, and we have WMAP, and we all consistently see these bumps. That is, this is what happens after we analyze the space, this distribution of hot and cold spots in the picture of the cosmic microwave background. So that's the picture from the prior page. See, it has a lot of error bars. This is what we get from Planck. Just, no, the error bars are dramatically smaller. And we do have error bars over here, and the reason we do is we only have one universe to look at. And by that I mean, if you're trying to measure what's the correlation in temperature between that spot, looking that way, and that spot over there, I can only make that measurement a few times. I can do it here and here, and you see. The number of angles available to me is very small, because I only have one universe to work with. Once you get to these smaller angles, I could start at this point and measure all the distribution. I can measure at this point and do all the distribution, and so forth. So this, we know we're not going to do much better below this dotted line.
What are the axes?
Okay, so here are the axes. This is a measure of angle with bigger angles here, smaller angles here, and this is the frequency of the magnitude of the variation in temperature squared. So you see, actually, if you look at this sideways, it says microkelvin. So this is a measure of how the temperature is varying as a function of the angular scale that you're interested in. So each angular scale, we do a mathematical experiment. That's why it's helpful to have thousands of people contributing there.
Are those logarithmic?
Yes. Oh, actually, no. This is not logarithmic, but it's a nonlinear scale. It's squared. Sorry, but notice how much better Planck is. The error bars are almost invisible. Now, what's this blue line? That's the prediction of inflation. If you take Alan Guth's model for the early universe and say there was an explosive increase in the size of the universe in the tiniest fraction of a second, and then the universe got into a kind of a growth phase, and now it's emerging into an accelerating growth phase. If you use his model, you get perfect comparison with the measured data. Does that mean Alan Guth is right? No. But he's not totally wrong. Let me show you something related. Look at this. Same thing. This does not have the Planck data. This is from 1997. So, the red curve is Alan Guth's prediction for what we should see of the cosmic microwave background distribution. Here's an alternate theory for the early universe called cosmic strings. Doesn't have these bumps. How about a model for inflation that doesn't have dark energy making the universe accelerate in its expansion? It has bumps, but it doesn't match the data. How about the yellow one, which is a different geometry? Is the open universe? Has bumps, but the position of the peaks is wrong. How about, there's one other here, isn't there? Yeah, no, I think I got it. So this is very suggestive that Alan Guth is on the right path. Now somebody talked to me during the break and basically said, do we know why the hot spots and cold spots appeared where they appear? And the answer is no. Let's go back to the drawing. Do we know why this is where they appeared on the sky? And the answer is no, we don't. The clue is there's a field of physics called quantum mechanics that says everything in the subatomic world is random, and that's probably why we inherited this distribution. In a different universe, the distribution might be different. But the point here is that the inflation theory, which I cover in lecture 2, explains away many problems. It explains away, so those of you who have seen the video, or if you have a chance to look at the notes, explains away something called the monopole problem. It explains away the flatness problem, and it explains away the temperature uniformity problem, and what's even better, it matches the data. Now, Guth's model, and in the notes, or in lecture 2, I have a picture of Guth's notebook, a picture I took at the Adler Planetarium in Chicago. And just for those of you who haven't seen the notes yet, I was there on business with NASA, and stayed at a nice hotel, Conrad, which is a Hilton property, I guess. And they have those books they have in the hotel, like advertising local restaurants and so forth. Hardbound book, they spend a lot of money to produce. And in there they have 2 pages on the Adler Planetarium, one of the world's great astrology museums. That's what it says.
Astrology.
Oh, you can't be serious. So they spent a lot of money to produce these fancy books, and got that part wrong. And I went to the museum. I don't know if any of you have been to Chicago. You go to the planetarium. It's out in the lake. There's like a peninsula, and the planetarium's out in the middle of the lake. And it was like, it was December. It was like the end of the world